required. The energy itself will go of its own. It goes there itself. All right, thank you. We all done? Okay, if you guys can just put those on the card, please. You give a round of hand for the sun and the earth. A round of applause for the sun and the earth. Okay, so radiation. How does this work? Well, let's take a look. You are welcome to sit.
Eureka! The story so far. Whenever there is movement and friction between two objects, you get heat. This is because the movement of molecules and heat are really one and the same. But we know that movement is a form of energy, so it follows that heat itself must also be a form of energy. That's why heat, just like energy, is measured in joules. And now, radiation waves. If you touch something that is very hot, you'll get burnt. This is because of conduction. The heat is conducted by a sort of domino effect from molecule to molecule, or from atom to atom, along the hot object and into your fingers. That's one kind of heat transfer. But if you hold your other hand above the same hot object, you will also get burnt. This is because of convection. The hot object causes the molecules of air above it to speed up. The hot air expands and becomes less dense, and is therefore conveyed upwards. That's a second kind of heat transfer. Are these the only two ways that heat can be transferred? Then why are you sitting under that beach umbrella? Because the sun's too hot? But how can the sun transfer heat to you? You're not touching it, so there can't be any conduction, can there? And since most of the space between you and the sun is just that, space, except for the thin layer of air formed by the Earth's atmosphere, there can't be any convection either, can there? Because once you get beyond our atmosphere, there's almost nothing out there to do the convecting. But the sun still feels hot. Amazing. How is that possible? Is there a third kind of heat transfer which allows heat to move through empty space? Yes, there is. And to understand it, you must first of all remember that heat is a form of energy. Now, energy can travel in various ways, but one of the chief ways in which heat energy travels is in the form of waves. Rather like the waves that a boat makes when it moves through the sea, or the waves that spread out when you drop a pebble into a pool of water, or the waves that travel along a rope if you jiggle one end of it up and down. In all these cases, what you are seeing is the effect of the movement of energy itself. By means of waves, energy can move through any distance. You can do it yourself. You can make that umbrella move without touching it. Tie one end of your rope to the umbrella, and now move your end of the rope up and down. You can actually see that your energy is traveling through the space between you and the umbrella, and then making the umbrella move. The heat energy from the sun travels like that. The sun sends out waves of heat energy in all directions. Each of them is rather like the spoke of a wheel, and this is exactly what scientists call them, only they use the Latin word for spoke, which is radius, from which they get the word radiation, the name given to this third kind of heat transfer. So it's by means of radiation waves that the sun can transfer its heat energy to you and make your molecules go faster and therefore make you hotter, even though the sun is millions of miles away. Just as, by means of waves again, you can transfer your energy to the umbrella and make it move, even though you're standing several meters away from it. But it isn't just the sun that radiates heat in all directions. So does an ordinary fire, or a stove, or an electric light bulb. In fact, waves of heat energy are radiated to some extent by all sources of heat. Even you radiate a certain amount of heat in the form of waves. Come to think of it, there are waves everywhere. Oh, watch out. Here comes a big one now.
All right, so write a summary. All right, so the radiation, they talked about the guy doing the barbecue. When I was in college, every year just before the week before the Army-Navy game, Army Week, big football game, it's our rivals. Well, the big pep rally, one of the big things is we would burn a Black Knight mule in effigy. Their mascot was Black Knight, and the mule was effigy, means basically you make a model of it and you burn it. I'm sure they were burning a goat up at West Point, because that was our mascot. But this bonfire, we set it up out in the field. We pile the wood up about 30 feet high, light this thing on fire, and if you stuck your hand in it, you would get burned. That's conduction. If you were way up above it and all that air that's rising up, all those sparks and everything else, you put your hand up there, that you get burned because that's convection. But if we were at the side and you would feel this intense heat coming off, this intense heat energy coming off of it, this was radiation. In fact, you couldn't get within about 30, 40 feet of the fire because it was so hot. So you'd be back and everything. But this is radiation. Everything gives off because basically what happens, everything absorbs visible light. So you absorb the visible light. Those Roy G. Biv colors. Like I said, most of the light that comes in from the sun is in the form of visible light. There's a few other things, but for the most part, it's just visible light. They will then emit infrared. So they take in visible, put back out infrared. Like your tables are absorbing visible, they put back out infrared. Now you guys are also absorbing some and laying some out, but you're also giving off infrared because your body's generating heat. But that's the way you're losing heat to the room. Some by conduction, and a lot by radiation. That's why, it's like you see the cop shows and they have the guy running away and they have the helicopter and you see the little guy shiny. They're using infrared cameras. And the infrared is just changed into visible light, but infrared, the hotter the object, the brighter it looks. That's how that works. But if you are to be a good emitter of energy, you have to be a good absorber. Obviously, if you can't absorb energy, you can't emit anything. So I have two Ewers. That's what these things are called. Pitchers, Ewer, same thing. It's a good crossword, puzzle word. So which of these two? Is it the black one or the white one that's going to be the good absorber and emitter? Black. Good. Bad. Black is a good absorber. It is also a good emitter. Because if you can't absorb, you can't emit. White is a very poor absorber. Which makes why it's good for being out in the sun. It's not going to absorb. It also doesn't have very much air. It's not going to emit very much either. Now, the thing though is to remember, black and white are not colors. They're not shades. One is all color. The other is the absence of color. Okay, thing is, now we're getting into this, we'll get more. Chapter 20 is all about color. What you have learned about color comes from art, which is color by subtraction. And we will talk about color by subtraction in chapter 28. But how color works and how your eyes work is something called color by addition. Okay? So color means you have a frequency. A frequency. In other words, if you looked at the spectrum, the Roy G. Biv colors of the rainbow, where is black and white? Or not there, the frequency. Radio, when you turn to 103.7 on your radio dial, that's a frequency. It's a color. It's a color you cannot see. Color, in physics, color is another word for frequency. In fact, when they say like stoplights and running lights on aircraft and ships and things like that, they will actually specify a certain frequency of color. Red of this frequency, green of this frequency, yellow of this frequency. Why? Because we all see color differently. It has nothing to do with color blindness. We just see color. Everybody sees color differently. You might all. So it's like when people say, that's blue, this is the light, this light greenish blue I want, and someone else says, no, this is the light greenish blue. They're both right, because that's what they see. But it's just the way our eyes work. But to be a good emitter, we have to absorb. So it's like my coffee. I have 2 coffee cups here. So I have my white coffee cup, and I have my brown coffee cup. Yes, I know it's brown on the inside. It's a Navy thing. Don't ask. Navy, we don't wash out our coffee cups. It's a Navy thing. That's coffee. That's like 40 years. Well, actually, it's about 2. No. Yeah, well, that's the tradition. Put it this way, the maddest I ever saw Chief get, is when a seaman who was cleaning up everything washed his cup. Well, let's just say that guy got to probably clean the bathroom for the rest of that deployment, probably with a toothbrush. Don't ask. It's a Navy thing. It's just what we do. There's no real reason. It's just that's. Anyway, between my white cup and my dark cup, which is going to keep my coffee hotter? So you might say, well, there's brown side. Well, the brown has to, then you have white. The white is not going to absorb energy. The white is not going to, it's also when the cup gets hot. I mean, the cup's going to get hot by conduction, right? Because it's in contact, but it's not going to radiate away as much as my dark colored cup. Same with my pitchers. If I want something to stay hot in my pitchers, which pitcher am I going to use? I'm going to use the white one because it's going to radiate out less. If I want to keep them cold, which one am I going to put it in? Still going to put the white one because it's going to absorb less energy and melt what's inside. Okay, so there's less energy transfer because the white is reflecting things, the black is absorbing. And we get a little more into this. And by the way, what they're going to talk here too also applies to chapter 28. This is why.
Eureka! The story so far. One of the chief ways in which heat energy moves is in the form of waves. Sources of heat, such as the sun, or a fire, or a stove, send out these waves in all directions, as if each wave were the spoke, or to use the Latin word, the radius of a wheel. This is why this third kind of heat transfer is called radiation. And now, the radiation spectrum. In